Welcome to section 4. We're going to be covering a number of different topics on data modeling that will help you to get the most of your MongoDB performance. First, we're going to learn about basic indexing. This shows how MongoDB uses Btree indexes to give you fast lookups of your data. Second, we'll look at relational versus documents. This is a video that will explore how MongoDB's document model opens up the design space and allows you to make different decisions on how you design your schema. Then we'll start looking at specific examples of that, including linking versus embedding. This is the trade-off between whether you want to embed a subdocument or link to a different collection. We'll then follow that up with a discussion on designing your database for sharding, so you'll be able to see how you can design your schema so that you'll be able to partition your collections later and scale up to very high workloads. Finally, we're going to cover advanced indexes. This will cover things such as covered queries, geospatial indexes, and full-text search. That will allow you to use some of the more advanced indexing features in MongoDB. So let's jump right into basic indexing. In this video, we're going to cover three main topics. The first is Btree indexes, so we'll cover what that means and how MongoDB uses Btree indexes. We'll then explain the explain command, which is how you can find out what MongoDB is actually doing when you ask it to query for a certain document or certain set of documents. And finally, we'll explore the issues that come up when you start to do sorted queries and how you can use indexes to speed up those sorts. So the first thing we want to cover is Btree indexes. So a Btree is a computer science data structure that allows you to do very efficient lookup of sorted data. So this is an example of a Btree that might exist for a dictionary of the English language. In this case, it has 3 levels of depth, and the first level is the root, and that covers all A through Z indexes in the alphabet. And then at the next level, we actually have 4 different nodes. And we have everything under A through G is stored in the first child, then H through M is stored in the second child, N through S in the third, and so on. And then in the third level, we have each letter stored individually. Now, some of the things that distinguish a Btree index from other trees that you might have seen in computer science are that Btree index is always balanced, and it has a fairly high branching factor normally. So in this case, this is just for the purposes of example, we only have a branching factor of 4 to 6. In a real Btree index, you'd have dozens or hundreds of entries in each level of the index. So that allows you to actually traverse down the tree very quickly. But the idea is a Btree allows you to find a particular place in a sorted collection of data very fast. So in this case, we can find any word in the English language through 3 lookups. We go down to we choose what the first level child is, then the second level child, and then we can get the document location directly out of that. So something to keep in mind when you're dealing with MongoDB and indexing is MongoDB indexes are sorted and tabular collections of data. So MongoDB does use a Btree to actually look up things in the index, but if you just remember that they are sorted, meaning that you're dealing with a sorted collection of data, and they're tabular, meaning you can have multiple fields in an index, but you don't really have the same rich documents that you've got with a MongoDB database. So everything is stored as rows and columns in the index. So let's do some examples using the IPython notebook so that you can actually see what sorts of things you can do with the indexing. So here we have our normal stanza that we begin all of our notebooks with, which is just to import PyMongo, get a connection to the database, and in this case I'm also going to go ahead and save the restaurants collection to this variable call. So I'll be able to just refer to call instead of typing out db.restaurants all over the place. So the first thing I'm going to do is just drop the indexes, make sure that we're starting off with a clean collection, and here I can actually say call.indexInformation. We can confirm that the only index in the restaurants collection is the ID index. So now let's look at the structure of this document again. We have a bakery here. It's got burrows, cuisines, grades, names, restaurant IDs, and an address. So let's say we want to do a lot of lookups by name. What we can do here is we can create an index on name, and that's going to allow us to find a particular restaurant by name very quickly because it's going to create this Btree index for us. So we can do creation of an index by name in many different ways. In PyMongo, we can say create index on name. We can also specify that we want it to be on name ascending, because remember Btree indexes are sorted. So we can say ascending, and 1 is just shorthand for ascending. You can also be very explicit about it and say pymongo.ascending. And in all of these cases, it's creating the same index. So If I tried to create an incompatible index, then MongoDB would have gotten mad at me and given me an exception. And in this case, all of these are the same command, so they're essentially creating the same index, so it's quite happy with that. So let's say we're going to try to find all of the Dunkin' Donuts in our database. So I'll go ahead and find all of the Dunkin' Donuts, and then I'll take a count of that. So we find out there's 200 Dunkin' Donuts. And now, just for the purposes of this example, I want to see how many different cuisines are represented by Dunkin' Donuts. You'd think it would be a small number of cuisines. In this database, actually not so much. So we have American, Armenian, bagels, bakery, cafe, donuts, Jewish or kosher, and other. So maybe we want to do queries that are a little bit more selective. 200 Dunkin' Donuts is tough to find the exact donut shop we want, so we'll go ahead and create an index on name and cuisine. And I'll drop the index on name. Well, let's say we don't actually need to do a lookup on cuisine. We just need to do a lookup on name. Turns out that having a compound index with name and cuisine is just as effective as having an index with just name. So if I do a find on Dunkin' Donuts and specify the cuisine, I can do that, and you can see that there's a single Dunkin' Donuts, which is Armenian. So now what I want to do is I want to show you how to use the explain command, because sometimes indexes can be a little bit confusing. You don't know exactly what MongoDB is doing under the covers. So this is how you can actually find out what it's going to do. So the first thing that we're going to do is just drop all the indexes again, and I'm going to find all of the Dunkin' Donuts, and do that query, and then I'm going to explain it. And what we get is an execution plan, or the explain output. So in this case, it's a very large document. It has a lot of information in it. So what I'm going to do is actually call out certain keys in this document. The first one I want to call out is the winning plan. So you actually look inside the plan, the subkey query planner, and then finally winning plan. And we see the winning plan is a call scan in the forward direction, and it's looking for where the name is equal to Dunkin' Donuts. So what this is actually telling us is that it's doing a full collection scan of this collection in the forward direction, and it's looking for things where the name is Dunkin' Donuts. Well, that's not very good. And the reason that I know that that's not very good is I can actually look down at execution stats and find out some performance information about this query. So I do this, and it tells me a couple of different things. You can compare different queries by looking at the execution time millis estimate. In this case, my database is so small that's not very meaningful. But what you can look at here is the docs examined key. So it says it had to look at 25,359 documents, and then if you skip down here, you find in returned to return only 200 documents. That's not very efficient. So it had to look at 25,000 documents to return 200. We can make this a little bit faster with an index, so we'll see how to do that in just a second. Now, the explain output's a little bit difficult to look through, so I'm going to make a little plan summary function here, just to grab out the winning plan and the execution stages, and that will we will be able to look at those that summary information right here. Okay. So now that we've got our plan summary function, let's try creating an index on name and rerunning the explain. So now, instead of having a winning plan, which is a collection scan, we have an IX scan. That's for index scan. And it's actually going to give you the bounds of the index and the name of the index that it's going to use. So in this case, it's using the name1 index that we just created. And we're looking at the index bounds between Dunkin' Donuts and Dunkin' Donuts. So it's actually looking at a single entry in the index. And so it does that, and we can actually look down here at the execution stages, and we see that in this input stage, the index scan has to examine only 200 200 keys. This is 200 keys in the index, and it's returning 200 results. And then once it's returned those results, it actually has to fetch the documents from the database as well. So very nice. We've reduced the number of documents it has to examine to 200. And if we actually look down here at the execution stages, we can see that we've got this nice little data structure, and it specifies that we've got actually two stages. This is a nested data structure, so we're going to update our plan summary function a bit so that we can see those all listed out sequentially. So we see that here there is the first thing that we do in execution stages is the index scan, and we're returning 200 documents there, and then we do a fetch of each document from the database. So very efficient, much faster than doing a collection scan. Let's see, what if we need to do a search for all of the Armenian Dunkin' Donuts? we do this, then we can see our first stage, again, is just going to be this index scan on the Dunkin' Donuts. We get 200 documents, 200 keys examined, so it's going to return 200 keys. And then on the fetch, we actually have to look here, and it says it in returned as 1, but docs examined as 200. So the fetch stage is not very selective. What it had to do is actually load all 200 documents, check to see, is this an Armenian Dunkin' Donuts, yes or no? And then if it's not, it would just discard it and not return it. If we want to make this faster, we can create an index on name and cuisine. And in this case, let me go up here and grab this query again, and we can see how the query changes. So we've got our name and cuisine, and I dropped the index on name. So here, if I paste this and we look at this query again, then we can see now it's a 2-key index. It's actually checking both the cuisine and the name. These are both equality queries, so it's just Dunkin' Donuts, and from Armenian to Armenian. So the index scan stage is actually only examining a single key. And now, when we come down here to our fetch stage, we see that we're only having to examine a single document to return a single document, so that's basically as good as we can get on that. Now, one thing you might be wondering is, why did I drop the name index before? Well, it turns out you can use an index for a query that exactly matches the keys in that index, or you can use it for any index where you just need a prefix of those keys. So in this case, we have an index on both name and cuisine. If we want to do a query that's just on name, we can use the name cuisine index just fine. And this is an example of that. So we go back here and we do our find where the name is equal to Dunkin' Donuts and explain that and look at the plan summary. We see that we're going to be using another index scan here, and we're scanning from Dunkin' Donuts to Dunkin' Donuts. And for cuisine, we're going from min key to max key, basically meaning that we're not selecting anything there. We're getting all of the different cuisines here. So here's our index scan. We examine 200 keys. We return 200. The fetch stage, we examine 200 documents, and we return 200. So again, we're just as good as we could be, and we were able to use the name cuisine index for that. So the next thing that I want to show is a range or a prefix query. So it turns out MongoDB does the same thing for range and prefix queries. It doesn't really matter which one you're trying to do. So for a prefix query, what I'm going to do is actually create a regular expression to look for anything that starts with Dunkin', has any number of characters, and then a space, and donuts, and that ends the query. So I'm going to find that name, and then I'm going to explain it and get the plan summary. So we see we've got a winning plan here. We look down to the execution stages. First thing that it's going to do is an index scan. And what it's going to be looking for is where the name is between Dunkin' Donuts and Dunkin' Donuts. So this is actually a regular expression scan. It's going to look for anything that starts with Dunkin'. That's what it's actually going to be using in the Btree lookup. And then once it finds that, it's going to keep on going as long as it matches that regular expression. And it's going to be a little bit selective here. So it's actually going to have to examine a few extra keys here. So here we've got our, let's see, keys examined. We've got 25,359. So it actually had to look at all of our keys. And then it returned 408 documents. And then once we have that, then we have their fetch. We've got 408 documents. There's no filtering going on here. And we get 408 results. So that was okay. At least it did most of its scanning in the index, and it didn't have to scan through the collection. So can we do better than that? Turns out we can. So let's look at all the different distinct names that it had to find. So it's Dunkin' Donuts with 2 spaces, Dunkin' Donuts with 1 space, Dunkin' apostrophe 2 spaces donuts, and Dunkin' apostrophe 1 space donuts. So apparently this data set is not very clean. So let's go ahead and drop that index, or drop these indexes, and then we'll create another index. But in this case, we're going to do cuisine and name instead of name and cuisine. So if we rerun this query, what we find out is that the winning plan is now a collection scan. Well, that's not so good. So now we're actually fetching all of those documents from the database, looking at each document, and making sure that it matches that regular expression. Now, why does it do this? The reason is that everything in the index is sorted by cuisine and then by name. So we can't actually be very selective by only looking at the index entries that start with Dunkin'. So if we want to make this selective, we have to actually put in a cuisine, a specific cuisine that we're interested in, and then we'll be able to use that index. So if I put in a cuisine here in my query, it's able to match that cuisine, and then it can use a query on the regular expression here. And if we look, we'll see that it's only examining 480 keys in this case, so much better match, and it's 344 returning. So it found some Dunkin' Donuts that didn't match that, or some things that start with Dunkin' that didn't match our regular expression, or that had the wrong cuisine. And then we finally do our fetch, and we've got 344 returned out of 344 examined, so that's good news, meaning that we didn't have to fetch a lot of data. So if we want to find a single document here, we can look and see what are some other fields we can query on, and we can see that we've got a zip code here, so it's address.zipcode. So let's go ahead and drop our indexes and create a name index, and we'll look at doing a range query now. So this is a range where we want to find all of the Dunkin' Donuts in zip codes 10460 through 10462. So in this case, I'm going to do that explain and then the plan summary, and we'll see that what we have is we have a forward index scan with the Dunkin' Donuts to Dunkin' Donuts, so it's only finding a single entry there, but it does have to look at 200 keys, and we're going to have to fetch 200 documents and then filter those. So we're actually fetching them, looking at the zip code, and then discarding the ones that don't match, and so we're actually returning 9. So what we don't want to do generally in a MongoDB query is have our fetch stage load a lot more documents than it actually returns, because that's inefficient. So in this case, what I'm going to do is I'm going to create a compound index on both name and zip code and see if we can do better there. Now, if I do this query again, I want all the Dunkin' Donuts in those zip codes, then we see that we've got a much better selectivity on our index scan. So we're actually going to be having these bounds from Dunkin' Donuts to Dunkin' Donuts. So we're doing an exact match on the first and then a range match on the second. So from 10460 to 10462. And so we're going to have to examine 9 keys, returning 9 results, and then we're fetching 9 documents. So again, just about as good as we can do for a query on all of the documents there. So very closely related to range queries is the idea of sorted queries. So in this case, I'm going to go ahead and drop my indexes, create an index on name, and then I'm going to do a sort on zip code and then explain that, and we'll see what MongoDB is doing in this case. So our winning plan is a little bit complicated, so let's look at the stages here. The first thing it's going to do is an index scan. So it finds all of the Dunkin' Donuts first, returns the 200 Dunkin' Donuts in our database. The next thing that's going to do is fetch those documents. So it fetches them, and now it's got 200 documents. Then it's going to generate sort keys. So in this case, it's going to extract out the address.zipcode field so that it knows what the sort key is that we're trying to generate. And then it's got to sort those things in memory. That result set in memory, so it does that. And then we finally get to return the result. Now this is actually not very efficient, because sorting, although sorting can be fairly fast, if you've got a very large data set, this can slow down your queries a lot, and you can actually use a specific type of index to do much better sorts. So here I'm going to go ahead and drop the indexes, create another index on name and zip code, and then I'm going to sort that, and we'll see what it can do here. Again, it's going to have an index scan. In this case, I didn't select any particular zip code, so it's from min key to max key, but if you'll note, it doesn't do a sort. It doesn't generate sort keys. All that it does next is fetch. And the reason that it can do that is because our index is sorted in the same order that we wanted our query results to be in. So the order that it's scanning through the index is going to be the order that's desired, so we don't have to do a separate sort. And that's what we want when we're doing sorting. We don't want to actually have to generate intermediate results and make MongoDB sort them for us. So what if we're trying to do both at the same time? In this case, what if we need to do a range of zip codes and I want to sort by Burrow? So if I do that, I'm going to get a pretty complex query here. Let's look at the execution stages. The first thing is an index scan, and we're going to be sorting, or we're going to be scanning through all the Dunkin' Donuts and those zip codes. So that one gives us 9 keys, and then it has to fetch the documents, generate the sort key. This is where it's looking at the Burrow, and then it can sort that, and then finally give us those results. Not very efficient because, again, we have this sort stage intervening. So what we can do in this case is we're going to create an index on name and Burrow, and then I'm going to go ahead and throw in the zip code as a third key. And it turns out that's going to speed us up a little bit more. So if we drop the indexes, create this index, then I'll try to do the same query and explain that. And what we see is we've got the first stage is going to be our selective stage. It's looking up the name and the zip code. And the Burrow, though, is in the middle here. So turns out that because the index is name, Burrow, zip code, we have to actually examine all of the different zip codes in here. So what it's going to do is actually examine, see, keys examined is 16. So that's all of the Dunkin' Donuts. So in this case, if we look at the execution stages, the first thing that it's going to do is an index scan, and it's going to look for all of the Dunkin' Donuts in these zip codes. And you note that the Burrow, it's got all of the Burrows listed there. So we're going to examine 16 keys, and it's only going to return 9. And that's because it had to skip over some of these extra ones where the zip code was wrong, but the Burrow was right. Once it's done that, then it fetches those 9, or it fetches those 9 matching results, and we're able to actually return those in sorted order. So finally, I wanted to mention the basic rules of thumb when you're creating these indexes where you're going to be doing sorting and range queries. So the order is that you need to do your exact matches first, your sort keys second, and your range matches third. So if you're going to do a query that contains all 3 of these, that's the order that you want the keys to be in your compound index. So the way that this trade-off works is that if you put sort before range, then you're going to have to examine more index keys. Your range could have been more selective, and then you'd have a smaller number of documents to examine, but it would mean that you'd have to have a separate sort stage, and you really want to avoid that. So if you put your range before your sort, you would end up with more stages, so we want to avoid that, so we'll do our sort before our range. So once again, your exact match fields come first, followed by your sort keys. Finally, with your range fields, they come at the very end of your compound index. So, some resources that you can look up for more information on this. One is the explain command, and you can see all of the different fields that we didn't cover in this. We can also look at MongoDB sorting with indexes, and it goes over the details of exactly why we want to use that same order where we're doing range queries and sorting at the same time. So in this video, we learned how MongoDB's Btree indexes work. We did a pretty deep tutorial into the explain command and seeing how we can use that to find out what indexes are being used by MongoDB. And finally, we saw how you can design your indexes for efficient sorting or efficient sorted queries.